That's me. I think I'm I'm supposed to give a presentation here. There it is. Hello, welcome to Devoxx. I don't know who has seen my talk last year here. It still was Java Day. So now we have Devoxx. Oh, very good. Yeah, familiar faces. Excellent. Because this talk is actually building on top of the talk that I gave last year. So if you've seen it, that's good. I'm trying to do something new today, and it looks like it works. It shouldn't affect you at all, but I'm tired of lugging my laptop around when I'm giving just a presentation that slides. So today I'm trying to present it from my phone. We'll see how that goes, okay? So my name is Chris. I work for Twitter. I was told it's very cold in here, but I still have to, wear my Twitter shirt. When I put my shirt on this morning, the yellow shirt, the sun came out. So, coincidence? I don't think so. So, Twitter has a not so small anymore VM team actually. So we grew in size from last year to this year, but we doubled in size. We now have 8 people on our team. And so we have a bunch of GC engineers. Then I'm a compiler engineer. We have 2 other people working on the compiler as well. And then on AUTOTUNE, we're going to talk about AUTOTUNE today. And I know this is a delicate topic here in Ukraine especially, and some other Eastern European, Russian countries. Who in this room has a Twitter account? Yeah, that's not bad. So who of these people who have a Twitter account are actually using it? Because I think that's more of the issue here. Yeah, right. That's what I thought. No, you guys need to start using it. Okay. So you have to tweet about this conference in general. Devoxx. I mean, that's a big step, right? You have a Devoxx conference here now. That's great. If you're going to tweet about my talk, add this hashtag #TwitterVMTeam so that my people know that I was here and how cool it was. And then tweet about all the other talks as well, the stuff you liked, stuff you didn't like, and then they also have the tweet wall, so maybe you'll show up there. I'm going to talk a little bit about myself. So again, I work for Twitter. I work on JVMs for over 14 years. And basically all these 14 years I was working on compilers. So that's really my thing. The time is not running, by the way. That would be cool. So I started to work at Sun Microsystems, started to work on Hotspot, C2, mainly C2. I was always part of the Hotspot compiler team, so I was fixing a lot of bugs. These are the 3 major things that I worked on at my time at Sun and Oracle. So I worked a lot on JSR292, so invoke dynamic method handle stuff. So I've implemented a lot of this stuff in the JVM and in Java. If it doesn't work, you could blame me, but a lot of people touched the code after me, and I like to believe that the code I wrote was perfectly fine. So then, important JEP 243 Java level JVM compiler interface, we integrated that in JDK 9 so that we have a Java compiler interface so we could plug in external compilers to the existing JIT compilers that are in Hotspot. And so this was necessary that you could run Graal on OpenJDK or Oracle JDK. And then also in JDK 9, and that's why we also needed JEP 243, we implemented ahead of time compilation. I don't know how many people actually know about this. You can ahead of time compile stuff, and it's basically a small command line utility that's written in Java, and it loads in your Java classes and then sends it off to Graal. And since Graal is also written in Java, it's also very simple. Compiles the stuff, spits out a shared library at the other end, and then Hotspot can pick that up. It's very different from, let's say, Substrate VM, native image stuff you heard of from Graal VM. But so this is around since JDK 9. And now I work at Twitter, greatest company on the planet, obviously. So for the people, I mean, this talk actually says Graal in the title as well, but I'm not going to talk about Graal VM. Okay, so if you came here to hear about Graal VM, that's the wrong talk. I'm only talking about Graal, the JIT compiler. Okay, it's a part of Graal VM. We had a heated discussion up in the speakers room right now with Oleg and a bunch of other people, what it really means. So anyway, I'm just talking about the compiler. All right. Most people know what Twitter is, right? So we run on microservices. We have hundreds of microservices. So these are, as a rather old picture, it's from 2016, but it's pretty much still accurate. So these are all the services we have, and you see who talks to who. That's how it looks like. And then we have, you know, thousands, 10,000s of instances of some of these services, and on heterogeneous hardware. So, you know, there's a lot of computing power in there, and we run a lot of different things. That's the most important thing here. So if you want to optimize for performance, especially, let's say, in a microservice environment, because you have so many different ones, the hands tuning doesn't scale, right? You cannot sit down every now and then and tune the shit out of it, because it's, oh, are we streaming this? Yes, I think we are. So I have to be a little careful what I say. So hand tuning doesn't scale. So you can handle a few parameters manually, the ones you know, right? But there's so many other ones you don't even know about. And then it's very time consuming, and then it's also error prone. But the problem is if your code is constantly changing. I mean, we at Twitter, some of our services deploy multiple times a week. The code is changing basically daily, right? And so the optimality that you're hand tuning is basically gone tomorrow. So that's the whole point. And so many services operate below optimality. And if we run many instances of one service and we have many different services, this just adds up. And so if we could tune them all the time, we could save a lot of CPU cycles and also money, just because, you know. So performance tuning in general, so you have a function of a bunch of parameters defined over domain X. So this is just an introduction a little bit. It's not too important. So, but you want to find a configuration that maximizes the function, right? And then it's subject to some predicates, right? It needs to still work, right? That's one of the most important predicates. If you tune it to a degree where it doesn't really run anymore, it cannot serve requests anymore, then you've gone too far, right? So you need a predicate or a bunch of predicates that tell you, yes, this is still working fine. So performance tuning in general is, you pick new parameters to test, and then you test it, and then you measure the performance, and the performance engineer says, oh yeah, okay, this looks like this, all right, maybe I'll tweak this a little bit over here and over there. And you go in circles, right? And that's the whole thing. That's the time-consuming part. And what you want to do is you want to switch out that engineer over there with some black box that you don't know about. That would be ideal. And so this talk is basically talking about this black box that we are creating at Twitter. So this is a technique from machine learning. It's called Bayesian optimization. And it's a method to find optimal, or maximum, whatever your predicates are. And it does this iteratively and efficiently, and it finds near optima in very few iterations. So that's important, because as I said, if your code is changing constantly, you cannot run this thing forever and find out what the maxima is. You need it in a rather short period of time. And so this works very well with nonlinear, multimodal, high-dimensional functions, and that's very important for us because the JVM has hundreds of parameters that you can tweak, okay? So I told you I'm a compiler engineer, so I hope there are not machine learning people in the room, because I really don't know what I'm talking about, okay? I know nothing about machine learning. Ramke is the guy. He knows everything about machine learning, and so he's given presentations about this stuff before. Please go to YouTube and listen to him if you want to know more about this, but these slides, the blue slides, I stole. And so we do a short introduction. I tell you a little bit about how it works, Bayesian optimization, because later when we look at all the results I have, the graphs, I think it's better for you to understand how this worked. Okay, so we have parameters that affect performance here at the x-axis, and y is then performance, and higher is better. And so we have a few points that we figured out. We run 3 experiments or evaluations, and this is the result. And then what Bayesian optimization does, it assumes, or it figures out somehow, don't ask me why, don't ask me how, it figures out a curve where it thinks that's how the performance graph looks like. And with a certain parameter values. And then there's some uncertainty around this whole curve, and this is the space that it explores, okay? And so, as you can see, the dotted line, oh yes, I should have mentioned this in the slide before, the dotted line is the actual curve that we don't know at this point in time. The blue one is what Bayesian optimization thinks it looks like. And the uncertainty then is what it calculates, okay? And as we can see, the way that Bayesian optimization does it, it takes the maximum that we have right now, the dot on the left, and you see all the blue area above the red line. These are the areas that the machine learning tells us to explore next, because it has the highest possibility that we get a better result than we already have. And so we do this. We take this point, and then we see, well, it's actually less than it was before. At the bottom, you see the expected improvement. And so the next expected improvement, the best one would be this one. And so we put another point in there. It looks like this. And then we see, okay, it's not better, so we have to go somewhere else. We choose this one. Yeah, it's roughly the same. And then we put one here. And we see, okay, we kind of reached the maximum here because there's no blue area above the red line here anymore. So then we try over here where the expected improvement is higher. So we go over there, we see, oh, that actually didn't work at all. So that space is basically now, the part, the black box, the machine learning part then tells us, okay, you don't really have to look in that area anymore. And then we look over there, and then we look over here, and oh yes, oh that's a very nice maxima. Then we have two expected improvements down here left, and then we do this one and that one, and then we know, okay, this one is the global optimum that we found. That's basically how it works. I hope that's kind of clear-ish. Watch the YouTube video. He explains it much better, but I don't really have the time to go too much into details here, but this is how it works. So the black box thingy, the Bayesian optimization part, tells us which configuration to try next. Because with a certain of confidence, it can tell us, okay, you will find a maximum at this point. Okay, that's pretty much it. So we like Bayesian optimizations for a couple reasons. It's non-parametric, that's good. It's robust, very important. It's extensible, that's very important for us because we want to tune very different things. And then it's been tested on many different types of real-world high-impact problems. There is, I don't have the time to tell the story now, maybe I can tell you later, but it's actually where this whole thing comes from is very interesting. It comes from ore mining, gold, just saying. Okay, so now I'm going to show you all the experiments. This was just the introduction for you to understand. The rest will all be performance numbers and graphs and stuff that we got out of Graal. So what is AUTOTUNE? I've mentioned the term before. It's basically BOAS. So it's a Bayesian optimization as a service. It's a service that we run internally. It's just a service that does whatever the blue slides just did, right? And we just query it. We say, hey, we just tried this with these parameters. Tell us what to do next. And so that's what it does. And then we have AUTOTUNE, and AUTOTUNE is just the framework that does the experiments. You start an experiment with AUTOTUNE. It runs one evaluation with some parameters, and then it talks to the Bayesian optimization service. And so they communicate, and then AUTOTUNE runs a bunch of evaluations until either it finds an optimum or you tell it to stop. It could do this pretty much forever, right? To find the optimum, there's always, but at some point you have to stop. I think most people know what Graal is. I just briefly say what it is. People know what a just-in-time compiler is? Okay. So the Java virtual machine hotspot has some compilers. There is, not to confuse with Java C, that's something very different. So a just-in-time compiler in hotspot takes Java bytecode and translates it into native code so that your application runs fast, okay? And so there are two existing compilers. They are called C1 and C2. You've heard of this? C2, yes, okay. So there are two compilers. One is called C1 or client compiler, and then the other one is called C2 or server compiler. You might have heard client and server before. There used to be a dash client, dash server. That's completely out of date, don't use that anymore. And so C1 is a high throughput compiler. It compiles code quickly so that you get out of interpreting bytecode and just run on native code. And then C2 uses then profiling information that's being collected during your run and produces your high performance, peak performance code. And Graal is that as well. So Graal is just a replacement for C2. And it's being actively developed by Oracle Labs. There's an official OpenJDK project for it. All of the source code lives on GitHub, so you can grab it and download it and compile it. It uses JVM CI, as I said earlier. And very important, Graal is written in Java. That's very important for you. I have another talk where I do a lot of demos and show people how to use Graal. And one of the most important things is that it is written in Java, so it has different properties to, let's say, C2 that is written in C++. It's just memory allocation works differently, and you know all these things. So if you're going to try Graal at some point, keep that in mind. Maybe watch my talk beforehand or read up on it, that you're not, someone just posted something on Twitter and said, oh, Graal VM stinks. It's because he measured warming up the bootstrapping part of Graal as well, so you have to be aware of this. Yes, this is it. I was already talking about it, but this is it. This is the one, how to use the new JVM chip compiler in real life. If you're interested in Graal and you want to run whatever you have, your applications at your company or even at home, your pet project, who knows, maybe you should watch this first so that you're not thinking Graal stinks. That's really not the case. You just need to be aware of actually only two things, okay? Good. So now we go back to auto-tuning this stuff. So which parameters are we tuning? Their Graal parameters are Java properties. And so there are three parameters I picked that we are tuning. There's one called trivial inlining size. It's basically the compiler. Do people know what inlining is? Yeah, okay. So inlining is you have a method that calls another method. And what the compiler does, if you call that method often enough, the callee, that's what it's called. I'm going way too deep here. But it's basically, you could, in the source code, let's say it's Java code, you could take that small method and just copy it into the main method. That's what inlining is. The compiler does this for you, and it only does it when it knows it's important to get better performance. So if it knows there's an advantage. So this is inlining, and so we have trivial inlining size, so it inlines very small methods all the time, because calling the overhead of calling them is sometimes bigger than actually just inlining the code and executing it inline. Then there's maximum inlining size. Up to a certain size, you don't want to inline anymore, because then you're blowing up your method size, and then there are other things that come into play, like instruction caches of the CPU and things like this. And then there's this other one called small compiled low-level graph size, and it's similar to the second one. It just uses different heuristics. I'm not going into detail here, but so the few people who remember my talk from last year, I did this manually, right? So if you watch this talk, this is not the one from here, but Java one, but I gave the same one here. I'm just showing you the slides again. So we're going to look at mainly GC cycles and user CPU time, because the escape analysis in the compiler and in Graal can reduce memory allocation, and so we reduce GC cycles. That's very important, and by producing better code, we also reduce user CPU time. So these are the two ones we're looking at most of the time. So when I did it, these three parameters you just saw, I hand-tuned. I was sitting down on a Friday afternoon, couple hours, I was hand-tuning them. Very labor intensive. this is what I got. So I got an additional 1.5% less of GC cycles to whatever 4.4% that Graal already does by default. And this was user CPU time. So Graal reduced user CPU time by roughly 13%. And then my hand tuning, I could reduce this by another 2. Okay, that was the maximum I could find. And I knew back then already that this is not the optimum. It was just, for me, I've exhausted my own personal space, so that was that. The configuration file for AUTOTUNE is basically, we tell it, please tune these parameters from this range to this range, okay? So I tune the trivial inlining size from 10 to 25, and the other one from 200 to 500, and 200 to 650. You don't really have to do this. You could technically say 0 to 1,000, right? Or 0 to 10,000, doesn't matter, because the tuning process, the Bayesian optimization, will figure out where to look anyway. The reason why I specified ranges here, because sometimes if you go with some values too far out, it completely wrecks your instance. I had instances that didn't respond anymore. I couldn't kill them or things like that. So I wanted to avoid this, and so I gave it ranges. My test setup, as the last time, was one dedicated machine per instance configuration. And this is very important that all instances receive the exact same requests, because it's not even the same number of requests, the exact same requests, because a tweet, and we are going to talk about the tweet service a lot, a tweet can be 1 character long or 280 characters long. And that changes dramatically the memory allocation, because for 280 you have to allocate more memory, and if you process a lot of tweets, that affects the memory allocation quite a bit. We still run on the same Graal version. It's rather old, but it still works great, and we do default tiered setup C1 and Graal, so we compile first with C1 and then later recompile with Graal. The standard, if you run Hotspot today, you do the same thing with C1 and C2. We just do it with Graal. Okay, here are the numbers. So experiment 1, I did 2. I took the tweet service. It's one of my favorite services. It's a Finagle Thrift-based service. Finagle is a framework that we developed at Twitter, and we open sourced it, so you can grab it if you want. It's an extensible RPC system for the JVM used to construct high concurrency service. You know, I don't know what it is, but I think it's useful, maybe. Important one, or the reason why I'm showing this, it's 92% Scala code. So basically all of Finagle is written in Scala. Then the objective, okay? So we need to tell AUTOTUNE what to look for, right? What do we want to optimize? And in our case, we want to optimize CPU's user time in seconds, okay? So we want to, and since AUTOTUNE is looking for a maxima, we have to do an inverted function of that, so 1 divided by the CPU you're using, and then you're looking for maxima, which is then the lowest CPU. This is the objective we have, that's all, nothing else. And then we have some constraints, and I've only used one constraint here for simplicity. You could use many constraints, but the one constraint I used was if we get throttled. So we are running in a Mesos Aurora system, basically, and then when you get throttled in our system, then you're using too much CPU or something like this, or something goes wrong, then you get throttled. And this is how we measure basic health, right? I should have used more constraints, to be honest, but I was watching the services very closely if they're actually running fine. So this one was enough. And yeah, threshold doesn't really matter. Okay, you might remember how my graphs look like. It's usually 24 hours of tweets. So this is 24 hours of requests per second of tweets. And you see, I restarted my evaluations. One evaluation took 30 minutes. That's not a lot, but I wanted to have results quickly, so I decided to just do 30 minutes. And for the tweet service or the services that I used, it's enough to get to a steady state, so I could say, yeah, okay, that's actually an improvement. So you see all the experiments or evaluations, and this is a graph of where you can see the user CPU time between the two. So we are comparing a baseline to the evaluation, basically, right? And so you see if the blue line, which one is which? Experiment is blue and the control is the orange, right? So if blue is lower than the orange, that's an improvement. If it's above, like here, it's worse, okay? And then the Bayesian optimization knows, okay, we have to look somewhere else. This is what it looks like, the 24 hours. This is a ratio, so you can see when it's below, that's good. It's probably this one is one of the best ones. And this is the result of an AUTOTUNE run, okay? So I did 44 runs, and the objective is in percent of CPU improvement. So technically, you see the top two are about 8% of improvement, and then we have 3 6s roughly. So this is the improvement we were seeing by running the tweet service on Graal with different parameters, and you see the parameters over here. And then there are also, that didn't do it, here we go. There are also some where I violated the constraints. So the parameters were just too much of inlining or whatever happened. I'm not exactly sure, so they were invalid. Only 3 is actually pretty good, but it doesn't really matter, right? If it violates the constraints, whatever, it gets kicked out and no one cares about it. Here are the charts of all the evaluations we did. This is a little difficult to visualize because it's a 3-dimensional space. And there's really no way to visualize this really good, because this point doesn't mean, oh, we used, what, 21 of this inlining size. There are 3 other parameters involved in this point that are changing all the time. So you keep that in mind. It's just like a 3-dimensional space we're exploring. You can see, if you squint a little, you can see a trend that it's slightly going up here. That's a little bit of an outlier, that one over there too. But yeah, you can see some trend. I'd like to say there's some trend. On this one, maximum inlining size, not really. It seems like it's flat. And then when we look at this one, we can clearly see a trend, right? So the default, what was the default value of this one? I think it was 300. That's way too low, at least for this service. Doesn't mean it's way too low for all the applications out there, but for this one it is. And then I took the best result of this AUTOTUNE run and ran another experiment to verify that we actually get this improvement. So I ran it manually, the tweet service here, and you see again, it's 24 hours. I'm comparing C2 in blue, orange Graal, and red is AUTOTUNE. So this is also Graal with the AUTOTUNE parameters, the first line you just saw in the results. And this is scavenge cycles, so the tweet service is using parallel GC. And these are the GC cycles we have. As you remember, and I've mentioned it before, Graal already gives you better performance and less GCs. So in this case, it's 3.4% less GCs that you do by just switching out C2 with Graal. And then if you bring in AUTOTUNE, we could reduce that again by 3.5%, which is great. Because if you remember, when I did it manually, it was only 1.5, right? So 3.5 on top of already 3.4 is amazing. By just tuning the compiler, we could double it, right? So we have 7% less GC cycles. And this is great because GC cycles always affect your latencies. This is the same metric, just in a different graph. It's basically how much bytes we allocated per tweet. Looks the same, it's pretty much the same number, 3.5, but you can see across the board over the 24 hours, it's pretty flat. So what we improved all the time. It doesn't matter, it doesn't depend on the load. So 3.47, okay. This one is always the most interesting one, at least for me. It's the user CPU time, because if you can save user CPU time, you can reduce your instance size, And that means you will save money. You don't have to spend so much money to run whatever you're running. In our case, we run Twitter. So if you switch over to Graal, you already save 12%. That's nothing new. You've seen that before. And then if we bring AUTOTUNE, it looks like this. We can already tell, okay, yeah, that's something. And it's another 6%. When I did it manually, I got 2. So 6 is, I was very impressed by this. And so that's combined 18% that you can save. So if you have, I don't know, 100 servers that you run your stuff, you can get rid of 18 of them because you don't need them if you switch over to Graal and tune it. Then the P99 latency is also very interesting. So if you can already see, yeah, this one's all right. You can already see that when you use Graal, because of the smaller allocation rate and less GCs and so on, and better, tighter code, our latency is already much better. And if we auto-tune it, you can also see, yes, there's an improvement here. It's a little hard to tell how much that is in this graph. So one thing I did was I integrated over the graph, over the 24 hours, and basically that difference over here is what we're saving. And we're saving already 20%. We have 20% less latency by using Graal. And then if we auto-tune it, we get another 8. So we can reduce our latency by 28% by just running this configuration, which means if you guys would use Twitter and tweet, you would get your tweets 28% faster. That would be nice. You should try it if it actually works. So I'm always using the tweet service because it shows the improvements really, really well. So I decided this time to also use another service called Social Graph. It basically, it's all the social interactions you have with other users, right? Who you follow and who follows you and all this stuff. So that's what Social Graph does. It's also a finagle thrift service. It's a centralized and useful abstraction for managing many-to-many relationships at Twitter. So that's what it does. Same thing, right? The objective, same again. It's just the name here is different from the instances that I'm running, but we look at user CPU time again. Constraints, exactly the same. We try to not get throttled just for Social Graph. That's what a Social Graph request per second looks like for 24 hours. And again, I did 30-minute runs for this one. This is the user CPU time graph that you already know from before, and you can already see this one's rather big here. There are a bunch of big ones in here. And this is the ratio part. Nice, nice. Well, wrong direction, but still nice. And the AUTOTUNE results for this one. So I again did 44 results, 44 evaluations. The top ones are in the 7% range. So that's already very exciting. And then, 766, so the top 5 are in the 6% range, so we can be pretty sure that's what we are going to see. Then constraints violated, in this case only 1. Don't ask me why 3 are still in progress. This AUTOTUNE is not production ready, let's put it this way. It's still, we're experimenting with it and we're still working on it, so some things can go wrong sometimes. And I'm sure something here happened. What's very interesting, I've not mentioned this before, let me go back one. When you look at the top 3, they're roughly the same improvement. But when you look at this number, it's very different. Like it's 23 and 12. So if you would do this manually, you would never guess this, right? This one, 650, 470, they're very far apart. It just depends on, I'm only tuning 3. What if you tune 10? It's like you cannot even fathom this in your head. And so, but this framework just figures it out for you. And these are the graph results, so it's pretty much the same as before. There's a slight tendency to be better when it's higher. This one again is all over the place. And this one, it's not as clear as with the tweet service. but you can still see a slight improvement if you go higher. And actually, this is very interesting that the highest value we've used is actually the best one. But again, it depends on 2 other values as well. So, same graphs as before. Requests per second looks like this for 24 hours. And then social graph is actually using CMS. So we're looking at parallel news cycles now. The improvement that we see by using Graal for social graph are not as big as with the tweet service. And that depends on your application, right? If you have a lot of object allocations that the compiler can eliminate, that's great, but it depends on what your code looks like. And in this case, it's not as much as the tweet service. And if we auto-tune, we get this graph, and that's very interesting because we can actually tune it so that we get more out of it by just switching over to Graal. You remember with the tweet service, it was roughly the same, but here's actually more. So we can reduce GC cycles by 5%. It's already great, again. The user CPU time for social graph looks like this. It's like a 5.5% improvement. That's roughly half of what we are seeing for the tweet service. And then we auto-tune it, and this is the result. The 7.8 I think I picked up here. It's very interesting enough. I didn't have time to look into this yet because you can see the improvement over here is not as much. And that actually shouldn't be the case. It should be flat over the 24 hours. So I have to look into why this is actually happening. But I picked up the 7.8 over here because I want to look good on stage, right? So don't look over there. So in total, it's 13. It's still great. I mean, and we have a lot of instances of that service, let me tell you that. So 13 is already amazing. Yes, right. So questions. And there's only one, it's usually more hands go up at this point in time, and let me ask the question for you and tell me if it's the question you had. Is that the question you had? You had that question, right? Yeah, no, most people in the room have the question. Okay, yeah, okay, well, Graal's cool, but have you tried it with C2? Of course I did. I mean, I'm not stupid. You think I would come up here and not have done it with C2? I would be embarrassed. So I did the same thing with C2. And I picked these 3 parameters. They're similar to the ones I used for Graal. So max inline level that does not exist in Graal really, but it's how deep it inlines. So if you have a call chain of methods and it's deeper than 9 levels, it stops inlining no matter what. So if you're using, and that's actually a big issue with C2, because these days everyone's using a trillion of frameworks and they call each other and call each other, and then so your call stacks are getting this and this deep, and then it stops inlining. It's not doing it anymore. Then there is max inline size. It's pretty much exactly the same as the other one that we looked at. The only difference is, and I'm spilling some very useful information here right now. These numbers are bytecode size, while for Graal it was the graph node size. So in Graal we parse the method first, and then we get a graph of nodes, and then we look at the number of nodes, but here it's only bytecode size. And so if you ever wondered, maybe you've heard it before, but if you ever wondered you had a small method and it always inlined and the performance was fine, and then you added a bunch of assert statements in your method and suddenly performance went to shit and it didn't inline anymore, that's because of this. Because C2 is not accounting for assert instructions that are actually not compiled, because it just looks at bytecode size. Very embarrassing, and we never fixed it. So, yeah, inline small code. So this one, it's also similar to the one in Graal, but this one is actually looking at native code size. So if if C1 already compiled a method, and the native code size is bigger than 2,000 bytes, it does not inline it anymore. If you ever ran a benchmark or whatever you have in your company, and you did benchmarks, and you've seen very different numbers on consecutive runs, it's mostly because of this guy. Because what happens is, if you have a method that's very, very hot, okay, you really want to compile this one, it probably calls other methods that are hot because of that one too. And then these methods get scheduled for compilations, and sometimes at different levels. And then it's a race condition in your compile queues. If the C1 schedule compilation for this hot method gets first, and then you do the C2 compilation, it's not inlined. If it's the other way around, if the C2 comes first, it's probably get inlined. That's where it's coming from. So Graal doesn't do that, I'm just saying. Okay, so the ranges are roughly the same what I used for Graal. So inline level, default was 9, so I go from 5 to 20. And then max inline size from 10 to 50, and then from 500 to 4,000. I just picked random numbers. So I used the tweet service again for this one. Requests per second for C2, 24 hours, same thing, 30-minute runs. Use the CPU time. This one looks interesting. Don't know what happened there. So we see there is definitely improvements here and there. And these are the results. So the best we can do with C2 is 5%. That's really the best we can do. And if you remember, for the tweet service with Graal, it was 8% already. And then I think what we got out of it, that's also something we still don't know exactly why, and we have to look into it. Because if you remember, the AUTOTUNE results for TweetyPie, for the tweet service, was about 8% in AUTOTUNE, but then only 6 when I ran it in my experiment. So if we kind of assume the same here, you see we have 1.5, and then we have almost a 4, and 3.5, and 3.2. So I would guess that these 5 would translate to 3 when I run an experiment, which I didn't do. That's the maximum we can do for the tweet service. And for Graal, it was, what, 18? So C2 is all right, but even with AUTOTUNE, we cannot get the same out of it as with Graal. And so going forward, for the future, and that's why we at Twitter moved to Graal, is because we can leverage the compiler much, much better. We can write our new compiler optimizations for it, and we can use stuff like this and have it on all the time. This is the bottom part of the table. Interesting for me here was not that it really matters, but like the worst result is 87. That's really bad. I think the worst result we got for Graal was 92 or something like this. So this was interesting, but it's basically just how Bayesian optimization picks the points. So I'm not exactly sure why it goes that low here. The charts look like this. Very, very interesting, this max inline level one. The default is 9, so we're here. And then you can see it should actually be 16 or 17, at least for this particular service. And then it's basically gets flat or even gets worse, because then I think your method gets too big, and then you see other factors come in. But it's very interesting that the whole world runs with 9, right? Probably not optimal, to be honest. This one's flat. Really doesn't matter. It seems like what size you pick here. And this one as well. So that was very interesting to me. I mean, again, remember, this is not one-dimensional, it's three-dimensional, but it gives you roughly an idea of how the compiler behaves. When we remember the graphs we saw with Graal, we almost always saw an improvement if we did more, because then if you inline more, you can, all the other optimizations that the compiler do, they have a broader view of things, and then they can optimize more. And with C2, it seems like it's limited. And I think that's mainly the advantage of using Graal. So it says 14 minutes. I don't think I have 14 minutes, but pretty much done. I haven't really mentioned, yeah, I mentioned it a little bit. I was not vehement about it. This is usually the summary of my talk. So all I want, and the reason why I'm giving these presentations is that you guys go back home or Monday at work and give Graal a try. Because I think that it's the future, and for most people, especially when you run Scala code, it will help you. It will definitely reduce your CPU consumption, and it will save you money. It will save your company some money when you do this. Please give it a try. Let me know how it works, either me or Oleg or the Graal VM team, or I don't know, let the Twitter space know how it works. I would be very thankful for this. I'm almost done. There's one more thing I want to do, and I'm not sure if I can do this here. So this will get interesting. Does this work? Yeah, it does. See? That's amazing. 1 second. I got it. Okay. I can only do it like this, but you can see it. So I'm doing, you guys know what an unconference is? You ever heard of J-Crete? Yes. I'm doing the same thing in January in Hawaii. I don't know. I've been in Kiev a bunch of times, but not in January. I'm just guessing the weather is cold. Am I right? So if you want to come, and since it's an unconference, you just register. You don't have to send in CFP or anything, right? If you want to come and discuss things with us, me, other Java developers, or whoever, there are a bunch of people already signed up. They will come. Just go to the webpage. I don't know if that's, you can see that. I don't know. Follow the Twitter account. It's like bit.do lava1, something like this. That's the only one I could get to work. If you want to come, book your tickets. Well, it's for free. Oh, I should have mentioned this. It's for free. So I made it so that the conference itself, the unconference itself, is free. The only thing is, if you're going to come, we do the unconference at a hotel, and so if you want to come, I beg you to book your hotel rooms with the hotel, because that's basically the way how we could make it for free. And this should be loading, but it's not, thanks to the Wi-Fi. Yeah, if you're interested, January 14th to 16th, that's your chance to come to Hawaii, really. And that's all I had. Thank you very much. See, someone followed me. Oh, were there questions actually, or?
Well, apparently I already have a microphone, so probably I will be the one. I'm not sure I've noticed, so you mentioned that, yeah.
Oh, sorry.
Thanks for the talk, first of all. Which version of Graal VM you are using? Is that community or enterprise?
Did you say Graal VM?
Yes.
We're not using Graal VM. So oh yeah, here, it slowly comes up. I had a slide, I can go back if you want me to. I had a slide where I said what JVMCI version, what Graal version we are using. So we at Twitter, we have our own JDK. And it's basically a clone of OpenJDK 8 update. And then we backported JVMCI to our JDK, and then we cloned an upstream version of Graal, the compiler. And that's all we do. We don't do Graal VM stuff. We don't, when people, and that's, is Oleg here? It's like this discussion we had up there. I said Graal VM is such a confusing term because it means so many different things. When you say Graal VM, I don't even know what you're talking about. Are you talking about hotspot? Are you talking about hotspot running with Graal legit compiler? Are you talking about substrate VM or truffle? What do you mean? And so we don't use all these other technologies. The only thing we use is Graal legit compiler.
Correct me if I'm wrong, they are different for community and enterprise versions, no?
That's correct, yes. But we are only using the community edition.
Okay.
Maybe that was your question.
Yeah, exactly.
Okay, yes.
Okay.
Then the open source version.
Okay. Have you ever considered using Zing from Azul Systems?
Not really. Any Sing people here? um, the problem.
I'm not from Azul.
No, the problem is, so Falcon is, you know Falcon,
Yeah.
like the compiler they wrote using the LLVM framework. That's a really nice idea on paper. But when I used to work for Oracle, we were looking into what technology could we use to replace C2. And of course, we also looked at LLVM. And the problem with LLVM is it was never designed to be a JIT compiler. It was always designed to be a framework for static compilers. So it's really slow. The throughput is very slow. The Azul, I shouldn't say this, but so they have two technologies. They had Ready Now before, and they're working on this new technology now. That I don't think they have a marketing name for it yet. They call it compiler stashing. It's basically they save compiled code from previous runs. And the reason they have to do this is because Falcon is so slow. I don't want to bash Sing here, but that's, unfortunately, these are the facts.
Okay, thanks for the
Sure.
answers.
There's one down here.
Hi, thank you for the great presentation, great talk. And my question is, do you try to tune also JVM parameters, I mean runtime parameters of JVM, not only compiler parameters? And how they correlate? Because if you inline some code, you can finish with huge methods which load into memory, and you have great work that need to be done by your garbage collection, for example. Just like example.
Yeah, these are not really related. So the code we compile, or the code cache, that has nothing to do with garbage collection.
Yeah, I mean, but it's put load on memory. It's loaded, and you have less memory for your heap, and then you need to GC to run more often, for example.
Yeah, but this is not at all. So the additional memory we are using, because we're inlining a little bit more, does not affect anything, right? We're talking a megabyte or two more. This is nothing compared to how big your Java heap is. This time, no. So to answer your question, no, I've not tried
but
to.
It's in general, but it's
you
like
can.
example, yeah.
Oh, absolutely, you can. That's what the AUTOTUNE framework was initially designed for, to tune GC parameters. And there was a talk by Romke 2 years ago, even already, I think, where they talk about one service where they tuned the GC. But since I'm a compiler engineer and I know nothing about the GC, I just do compiler stuff. And the two, you can use them together, obviously. Sure, you can tune the compiler and you can tune the GC. There's probably way more improvement possible by tuning the GC. One thing I would like to add here, it was not really a question, but it might be important to some people, or interesting, because you were talking about memory, right? And everyone's running in a container today. So your container, you have, I don't know, 8 gigabytes of memory or something, and then you give your Java heap 6, because the rest you have to allocate for the JVM to load in stuff, and very importantly, compile methods. So so C2, since it's written in C++, it will allocate memory on the native heap with malloc. So you have to reserve memory on the side, and sometimes compilations can be quite big. Compiler graphs can grow up to the hundreds of megabytes of memory. If you run with Graal, it's allocating memory on the Java heap. And you should watch this one talk that I give, how to use the JIT compiler in the real world, because that's the real world. In a real world scenario, almost all of your compilations happen at the very beginning of your application startup, like the first 30 seconds, the first minute or two. And at that point in time, your application is not using all of your Java heap, because it's not even fully up yet. And you probably, you start up your thing, and then it connects to other services, and then maybe it warms up itself a little bit. At that point in time, you've already compiled everything. So if you run with Graal, you can basically take more memory and give it to the Java heap. And then later on, when you're not compiling stuff anymore, your application has more memory. You didn't really ask that, but I think it's important for people to know.
Yeah, okay, thank you. And may I ask another question about data processing? Do you use Apache Spark at Twitter, for example? I mean for data processing? Or Hadoop or more something like that?
I know we use Hadoop, but I have no idea.
So you don't know about optimization
No.
of this stuff? Okay, thank you.
More questions? Yes.
I have a two-part question.
Yeah.
So first part is, if I understand correctly, I just want you to confirm it. We probably need to auto-tune parameters on every release, or at least every major release, because code may differ. So
Yes.
yeah, and the second part is, you mentioned that this 24 hours test scenario should be the same every time. So is it possible that you just overfit your results to this one specific scenario?
So the first part of your question, so as I said, this is still very early, and it's not our top priority to work on this tool. So it's, some people ask me, oh, is this open source? And my answer is always, we want to open source it, but at this point in time, it's ridiculously hard to use. Okay, so it's very experimental. The goal of AUTOTUNE is that we have this on all the time in production, that the services tune themselves basically all the time.
Continuous integration.
Exactly. And then the question is, and we don't have the answer to that yet, because I think we have to try it, and it will be different for different services because they behave differently. For this one or for these two, 30 minutes was okay, but for others that might not be good enough. Maybe for some services, one evaluation has to take a day, because just the fluctuations over the day are too different. I don't know. So our goal is to have this on all the time, and then it depends on the service. We were just talking last week in San Francisco about this, and Romke said, well, maybe one evaluation, one experiment, one tuning experiment should take a month. You know, and then you run your evaluations a day or two to really know if it helps or not. So I don't know the answer to that yet, but I'm guessing in that range. And yes, the code changes pretty much every day, but not as dramatically. So, but there are more factors coming into play, because if you do it a month, the code changes from day 1 to day 28 a lot. And then, so I don't know. And the second part was?
About overfitting. So you use the same scenario for your testing. Maybe your parameters that you see as best parameters, maybe they're just overfit to this specific scenario.
Oh, absolutely, yes, totally. And especially, I'm not sure what you mean when you say scenario.
What you test, you said that you need to send the same tweets every time, because
oh yeah, right.
So it's not random. You need to see the same results, that they correlate.
Right. The reason why I have this set up like this is because I only run one instance. So the goal, when AUTOTUNE is continuously running in production, to have many more instances run the same parameter, and then you use statistics to filter out all the, you know. That's basically how it should work.
Yeah, thank you.
Last question. Any questions about Lava 1? So January, if you've never been there, it's summer. So it has probably 28 degrees. And the water also, just saying. Okay, thank you.